Hello, hello. Okay, so hello, good evening. Apparently, I'm recording at night, no? So anyway, so by the time you watch this video, I think umaga na, no? This will be the last part of the chapter 6 discussion in the laboratory, which is on electrochemistry, no? So in our previous discussions, we were able to cover this, and so we were able to cover all those topics, no? And we will be left with the last two topics. Okay. So let's recall what we did last time. So last time I left you an activity which is to balance redox reactions. Okay. So I hope you were able to convert this into cell notation form, and I hope that you were also able to balance redox reactions. Anyway, the worksheet has been uploaded on Canvas, so just go to um, announcements, then look for the post that has a title of a title and um, additional worksheet materials. Okay, so please download that. Okay, I also gave an explanation in there so that you can read this. You can read that and fully understand what's happening in the problem. Okay. So anyway, I left you last time with this topic. Okay, so standard potential. So basically, what you're going to do is to identify which is the cathode and which is the anode. Okay, once you were able to identify which is the cathode and the anode, then you can look for their potentials here. Okay, so their cell potential can be obtained from this table. Okay, so for example, last time I gave you this activity. We knew that this is the anode and this one is the cathode. Okay, so to solve for their cell potential, we look first for the potential of the anode and the cathode. Okay, so for this part of the reaction, that just look for the species on this table that contains zinc and zinc 2 plus. Okay, so just look at the table and look for those ions, which is this one. Okay, so it has a potential of 0.76 volts. And then for the copper 2 plus copper, so again look at the potential table to find their to find its potential. Okay, so apparently this is 0.15 volts, and then solving for E cell is very easy. So once you have the potential of the anode and the cathode, all you have to do is to subtract them. Okay, so the formula that we will be using is the E naught cathode minus E naught anode. Your lecturer may tell you that the equation is E right minus E left. Okay, so your lecture instructor may tell you that. However, um, it is also the same with the one I'm giving. So that's cathode minus anode, because remember, on the right side of your electrolytic cell, you have your cathode, and on the left side, you have your anode. But again, I emphasized last time that uh, I want you to know what is on the right and what is on the left. Okay, so that uh, you will not be lost. Okay, so always remember that those on the right are the cathodic reactions. Basically, those are reduction reactions, and those on the left are the anodic reactions, or those who undergo oxidation reaction. Okay, so anyway, uh, I gave the answers for these questions in the worksheet anyway, so I will proceed with the last two topics. Okay, so for the first part, we're going to talk about the equilibrium constant and the free energy. Okay, so if you could recall your general chemistry in senior high school, remember that the free energy is the measure of spontaneity of a chemical reaction. That means if G is negative, or delta G is negative, that means the reaction is spontaneous. But if delta G is positive, that means that the reaction is non-spontaneous. So when you say spontaneous reactions, these are reactions that are going to happen instantly, okay? And those delta G with positive or non-spontaneous reactions, those are reactions that requires external force in order for the reaction to happen. Okay, so in electrochemistry, the relationship of free energy and the E cell is given by this equation. So that's delta G equals NF E cell. Okay, so what is Ne? Okay, so Ne is the moles of electron. Remember that when we are balancing chemical redox equations, let's be specific. When we are balancing redox equation, on the last step, we cancel the electrons. Okay, so the number or the coefficient of that electron being cancelled on the last part of your solving process is the mole of electron that we are pertaining to. Okay, so in Tagalog, yung kinakancel yung electron sa dulo, yun yung ilalagay mo dito sa Ne. Okay? So for example, you canceled 5 electrons on both sides. That means Ne is 5. Okay? Kung ano kinancel mo, yun yung ilalagay mo dyan. Okay? That's why electrons should be the same in number. Okay? Not because kailangan silang makancel lang, but also because to be consistent. Okay? Para alam natin kung ano ilalagay natin, it should be one value lang. Okay? So, hindi pwede 3 muna, then mamaya 2. No. It should be 6, diba? You always get the LCM. Okay? So, that's Ne, the moles of electrons. Yun yung kinakancel sa final step. F is called the Faraday's constant. Okay? Faraday's constant. This is used in physics, actually. But also, since this is chemistry, then we have to use it. Okay? So Faraday's constant is a value of 96485 coulombs per mole. And expressing coulombs in other units, that can be written as joule per volt mole. Okay? And then, E cell is the potential of the cell. If the potential of the cell is standard, then we have to indicate these small circles on the top. Okay, so remember, if we have standard condition, so if we have a standard condition, we always have to put a small circle on the top, and that is called a knot. Okay, that is called a knot. So when I say delta G naught, that means I am referring to standard free energy. When I say E naught cell, that means I'm referring to the standard cell potential. Okay, but if you don't see any circle on the top, so that means that is a non-standard condition. Okay, when is a condition standard or not? Okay, so we will know that if our condition is standard, if 1, if the concentration is equal to 1 molar. 2, if the pressure is 1 atm, or 3, if the temperature is 25 degrees Celsius or 298.15 Kelvin. So those are the conditions that has to be met in order for you to tell whether a condition is standard or not. Okay, so a condition is standard if they meet all these criteria. Okay. However, if they specified concentrations other than this, then that means it is a non-standard condition. Okay. Okay. So also in thermodynamics, if you could still recall your general chemistry, we knew that delta G is related to the equilibrium constant, given the equation delta G equals negative RT ln K. Okay. So this time it doesn't matter whether that's standard cell potential, I mean standard free energy or non-standard free energy. It doesn't matter. Okay. So they are both equal to RT ln K, wherein K is your equilibrium constant. Then given those equations, let me rewrite the previous equation again. Negative NF E cell delta G equals delta G naught equals negative NF E naught cell. Okay, so given all these conditions, then we can tell the relationships among these variables. Okay, so let's go with the first one. If delta G is negative, that means the reaction is spontaneous. Therefore, it will produce the products. Okay, so it is spontaneous, and the reaction will produce products. Okay, so what are the requirements for delta G to be negative? Okay, so based on the E cell, if your E cell is positive, then your delta G is negative. Okay, so think of it as this multiplied by a negative sign. So if this is positive multiplied by a negative sign, then all of this will be negative. Okay, so that means our E cell should be positive for delta G to be negative. Okay, so whenever we have a positive E cell, we have a negative delta G, meaning we have a spontaneous process, and the reaction will favor the formation of products. As a result, also, if your delta G is negative, your K value will be greater than 1. Okay? So if you do some algebra here, you will derive that K should be greater than 1 in order for G to be positive in value. Okay? If delta G is 0, that means we are at equilibrium. So we are at equilibrium. That means we have a balance in the system. So when delta G is 0, that means E cell should also be 0. Okay? So remember that moles of electron has a numerical value. The Faraday's constant has a value. So that means for this to be 0, E cell must be 0. Okay, so that's why if E cell is 0, delta G would also be equal to 0. And then solving for K using this equation, so just do some algebra, you will solve that K should be equal to 1 for this to be 0. So if we have 0 delta G, that means we have an equilibrium state. Nothing significant is happening in the system. And then we have this one, okay? So if delta G is positive, that means E cell is negative, okay? So so that should also be true, because if you have a negative value here multiplied by the negative in front, okay, so negative times negative will give you a positive product. Okay, so that means if E cell is negative, then delta G is positive according to the equation. Okay, so since we have a positive delta G, that means that the reaction is non-spontaneous. So the reaction is non-spontaneous, therefore it will not produce products unless you provide external force. Okay, so what I mean by providing external force, you may either heat the reaction or apply electrical voltage to the solution. Okay, so those are the external forces that are needed in order to make non-spontaneous reactions spontaneous. Okay, it will require efforts. Okay, so if your delta G is positive, that means E cell is negative and your K is less than 1. So that means it is less than 1. Okay, so it is decimal in value, or at least 0 if that's on the extreme positive delta G value. Okay, so that means it will favor the reactant mostly. So only few of the products, or at least no products, will be formed. Okay, because it is a non-spontaneous process. Okay, so I will answer just some few of these questions. Okay, so I actually uploaded the answers for this in the worksheet. Okay, but let me explain how to solve some of them. Okay, especially this item here, and maybe this item here. So I'm going to solve for their delta G and K. Okay, so let's get started. For number 4, we have this cell notation. Okay, so we have this cell notation. Typically, cell notations are written as metal, then ions, right? Okay, metal, ions, or gas. But in this problem, we have an ionic compound. Okay, so the ionic compound should give you an idea what is the charge of your metal ion. Okay, so it should give you an idea about the charge of your reacting species. Okay, so since gold is the reacting species on the anode, then that means I should get the charge of the ion form of gold. Okay, so I can do that by doing reverse crisscross. Remember that the 3 belongs here, the 1 belongs there. Oops, sorry. The 1 belongs on the other side. Okay, so since gold is a metal, then 3 will be positive, and that means -1 for the other species. Okay, so that means we can simplify this as AU single line, AU3 plus. Okay, then we have the salt bridge. How about calcium nitrate? Okay, so since our reacting species on the cathode is calcium, then that means I have to get the ion form of the calcium, which I can get by doing the reverse crisscross. Okay, similar to what we did earlier. So the 2 belongs to calcium, the 1 here belongs to nitrate, so calcium is a metal, so that's positive, this one is negative. Okay, so that means calcium nitrate can be simply written as calcium 2 plus. And then we have calcium. Okay, so whenever you see cell notations that are written in this manner, so all you have to do is to just get the ionic form of the reacting species. Okay, so that's usually written for metals. Okay, so you don't mind of the other chemicals there. Okay, anyway, so since we have now identified this is the anode, right? So this is the cathode, then we can look up for their cell potential. Okay, so this is the anode, this is the cathode. Let's look for their cell potential. So let me go to the previous slide we had earlier. So let's look for gold AU. Where's gold? So okay, so this is gold. So that's 150. Okay, and then we have calcium, so 150 for gold, then calcium will be -287. So gold is positive 1.50, -2.87. Okay, but take note of the reactions written. Okay, so the reaction for gold here is that it requires 3 electrons. Okay, so it requires 3 electrons. Then for calcium, it requires 2 electrons. Take note of that. Okay. Okay, so we can actually solve for the E cell. Okay? So we can actually solve for the E naught cell. That's E naught cathode minus E naught anode. Okay. So the cathode is -2.87 and the anode is -1.50. Okay, so let me subtract those numbers. -2.87 minus -1.5. The answer is -1.37 volts. Okay, so it is -1.37 volts. Okay, so we have solved for the E cell. Okay. I'm sorry. So it is not negative pala. Duling na naman. So it's my -2.87 minus 150. I'm sorry for that. I'm kind of sleepy, but I have to push this through. Okay, so it should be 4.37. So it should be 4.37 volts. Okay, so we now solve for the E cell. Okay, so that is what we need in order to get the delta G. Okay, and K. So let me erase this. I need more space. We have E naught cell for number 4, which is negative 4.37 volts. Okay. Remember that in solving for delta G, the equation is negative N F E naught cell. Okay. Remember that. We now have E cell. Okay. So that can be simply calculated by subtracting the cell potentials. F is a constant, that's Faraday's constant. But what is E? Okay, so what is E? I mean N. What is N? N is the moles of electrons. Okay. Do we know the moles of electrons? Not yet. Okay. So how are we going to solve for that? Okay. So basically, let's go back with our equation. Let's go back to our equation here, the cell notation. So in order for us to get the moles of electron, the N, okay, so we have to write this cell notation into equation form, okay? So that means I'm going to balance this, okay? Remember our technique? So this is the anode, right? So this is the anode. The reaction is from left to right. This is the cathode. The reaction can be written as left to right as well, okay? So in the anode reaction, I have Ag to Ag3 plus. Balancing this, I need 3 electrons, okay? And then for the cathode, I have calcium 2 plus. And then on the right side, I will have calcium. Okay, so balancing this, I need 2 electrons. Okay, so before I combine them, always remember that the moles of electrons should be equal. So you have to get their LCM. So what's the LCM of 3 and 2? That is 6. Okay, so that means the moles of electron has to be 6. Okay. So in order for this top equation to be 6 in number of electrons, I have to multiply it by 2. And then this one has to be multiplied by 3. Okay. So that means my equation can be now written as 2Ag plus 3 calcium 2 plus 6 electron. Then I have 6 electrons here as well. 2Ag 3 plus, and then I have 3 calcium. Okay. And then again, you cancel the moles of electrons. Okay. So yeah, so that's the moles of electrons, which is 6. Okay. And that is what we are going to plug in to this equation. Okay. So again, to get the moles of electrons, all you have to do is to balance all this equation. So in the prob set, I have not shown the balanced form, okay, but I have written there the moles of electrons, okay. So when you make sure that when you balance them, you get the same moles of electron as I did in the worksheet, okay. However, if there's any discrepancy, just let me know, okay. So now we know that we have 6 moles of electrons here. Okay, what's next? What's next? Then let's plug in all our given. So delta G naught equals negative 6 moles of electrons. Okay. F is the Faraday's constant, which is 96485 joule per volts mole. And then E cell is negative 4.37 volts. So you can see the moles will cancel, the volts will cancel, giving us the final unit joules. Okay. Okay, so just multiply all of this. Take note that we have a negative E cell and then we have a negative sign in front. That means delta G is a positive quantity. Okay, so that means this reaction is non-spontaneous. Okay, so so in joules, the answer will be 2529,836.7 joules. Okay. However, usually energies are reported in kilojoules. Okay, so we have to divide this by 1000. So this is 2529.84 kilojoules. So that's how you get delta G. Okay, it's very easy. You just have to balance the equation, look for the moles of electrons, solve for the standard cell potential, then plug them all in the equation. Okay. So now let's solve for the K. Okay, so let's solve for the K. How will we get an equation for K? So that's easy actually. So let me derive the equation to be used to get K. Okay. So remember, let me derive first. Okay. Solving for K. Remember that delta G is equal to negative NFE. Okay. It doesn't matter whether that's standard or non-standard. They have the same equation. And also remember that delta G is equal to negative RT ln K. So if this, where's my cursor? If this is equal to this and this is equal to this, then that means this is equal to that, right? Okay. So yeah, that's true. So we have negative NF E cell equals negative RT ln K. Cancel the negative signs, right? Make them positive. Okay. So we have NF E cell equals RT ln K. But we are looking for the K, right? So we have to remove that. Okay. So first thing first, we have to divide we have to divide both sides of the equation by RT. So we have an NFE cell over RT, and then we have ln K. What is ln? Okay. So ln is called the natural logarithm. This is the natural logarithm. So it is similar with logarithm. However, in logarithm, its base is 10. Usually, its base is 10. But for natural logs, its base is e, the Euler's number. So this can be written as log e. Okay. So that is quite different with the typical log function, which is just log base 10. This time, if we have an ln, that is log base e. Okay. Anyway, so that means in order for us to get k, we should pull it out from the log from the ln function first. Okay. So remember, let me write here. Remember that if we have log of x and we want to get the x out of that, what we're going to do? Okay. So what we're going to do is to apply the anti-logarithm. So we are making this equation an exponent of base 10. Okay? So we will write this as 10 raised to log x, 10 raised to y, and we know that log and 10 will cancel out, and then we can get x. Okay, so x is equals to 10 raised to y. But for natural log, we have the same process. Okay, but different base. Remember that that ln is base e. So instead of using 10, we have to use the e, the Euler's number. E ln x equals to ey. And just like the log, e and ln will cancel out, giving us x equals e to the y. Okay. So that means in order for us to get k out of the log function, a natural log function, we have to make this equation an exponent of e, the Euler's number. E, or the Euler's number. that is named after a very famous mathematician, which is, you know who? Euler. Okay. So that was named um, in recognition of him. Anyway, so now we know how to pull out. Mm-mm. Now we know how to pull out the ln function, how to pull out the k from the ln function. Then let's apply that concept into this equation. So again, we are making this an exponent of base e. Okay, and you know that e and ln will cancel out, giving us k is equals to exponential nf e cell over rt. So this is the equation to be used when solving for k. So now we now have an equation to solve for k. So let's do that. Let's solve for the k. K is equals to e rt. I'm sorry. It should be nfe over rt. So let me go through some details first. Again, n is the moles of electron. F is the Faraday's constant. E is the E cell. What is R? R is a gas constant. However, it is different with the 0.08206 liter atmosphere per mole Kelvin constant. We are going to use a gas constant that is in energy form, okay, which is 8.314 joule per mole Kelvin. And T is the temperature in Kelvin. If not stated, this is usually 298.15 Kelvin or 25 degrees Celsius. If not stated, that's usually 25 degrees Celsius. So now we know the variables necessary to solve for k, then let's plug them all here. So k is equals to exponential moles of electron is 6 times the Faraday's constant, 96485 joule per mole Kelvin. I'm sorry, joule per mole volts. Sorry for that. And then we have E cell, which is negative 47, negative 4.37 volts. Then on the denominator, we have 8.314 joule per mole Kelvin. And then we have T, which is 298.50 in Kelvin. Again, if the temperature is not stated, just use 25 degrees Celsius because we are assuming that we have a standard state system. So now just plug it into your calculator. Let me do that for you so you will know how to plug that into your calculator. And let me just open up my software. So allow me to type it here. So if you have a Casio calculator, just follow me. So Euler's number is usually on top of the ln function. So you press shift, then the ln. So you'll get this symbol in your calculator. This is the exponential function. This is what we need. Okay. So we have a fraction there, and then we type in 6 times 96485 times negative 4.37 divided by 8314 times 298.15. Okay, so our k is 0. It's actually not 0, but it is approximately equal to 0. Okay, so it is approximately equals to 0 because according to calculus, if the Euler's number is negative in exponent, then it will reach an asymptote. Okay, so it will reach the horizontal axis, which has a value of 0. Okay, so that's the answer. K is approximately equal to 0. Okay, so basically the reaction is not going to happen. So the reaction is not going to happen given that the delta G is positive, okay, and K is 0. Okay, so that means the reaction is not going to happen. It will only happen when you provide electricity onto it. Okay, so if you provide enough uh, energy for this reaction, then it will proceed. But if you don't provide enough energy for this reaction, then nothing will happen. Okay. So that means when you mix gold and calcium, nothing will happen. Okay. Nothing will happen. Well, let me solve number 5. Okay. So let me solve number 5. Uh, so for number 5, we have that equation. Let me balance first the equation. We have Sn2 plus, comma, Sn4 plus, double line Hg2 plus, Hg2 2 plus. Okay, so what you can notice is that instead of using a vertical line, we use a comma. Okay, so we only use vertical line if we are separating two different phases. For example, this is solid, this is ionic. Okay, so this is liquid form. So we need to use vertical lines. However, if they are both in aqueous form, and then we use comma. Okay, so this is an aqueous form, this is also an aqueous form, so you don't need to use the vertical line. Instead, you use a comma. Okay, and then the same thing for this one, but always take note that the salt bridge has to be written always. Okay, so don't forget to write the salt bridge always. So again, a comma is the same as the vertical line, except that this tells us that these two are in ionic form. Okay, so again, let me zoom it here. Okay, so take note that on the left we have the anode, on the right we have the cathode. So let me balance the equation. So on the left we have Sn2 plus going to Sn4 plus. Balancing that will give us 2 electrons on the product side. And then for the cathode, we have Hg2 plus. And on the right side, we have Hg2 2 plus. So we have to balance first the mercury. So we have 2 mercury atoms here, 1 mercury atom here. So balance that. And then now, let's solve for the charge. So the total charge on the left is 2 times 2, which is 4. And then we have 1 times 2 on the right, which is 2. So we have 4 charge here and 2 charge here. Positive 4, positive 2. So we're going to place electrons here. Okay? 2 electrons to make the charges equal. So there you go. Mole of electron is equal to 2. Okay, so I'm not going to write the entire equation. Okay. So let's solve for delta G. Delta G can be calculated as negative NF E cell. By the way, we forgot to solve for the E cell. Let me pull up the values for the cell potential of tin. So according to the table, this is 0.13 volts. And this one is 0.92 volts. Okay. Solving for E cell, let me solve it here. E cell is equal to, let me zoom it here. E cell is E cat minus E anode. Okay. 0.92 minus 0.13. So the difference is 0.79. So we have 0.79 volts as the E cell. Okay. Given that, we have negative 2 moles. The Faraday's constant 96485 joule per mole volts. And we have E cell 79 volts. Take note that the E cell is positive. That means the delta G should be negative. Okay, so it should be negative. Let us express this in kilojoules. Okay, 6.579. Dividing this by 1000, I will get 152.45 kilojoules. Okay, given that, we can proceed solving for K. The K can be calculated as K exponential NF E cell over RT. Okay, so plugging in, so we have 2 times the Faraday's constant, 96485. I'm not going to write the units because you know they will all cancel out eventually. Okay. So the E cell is 0.79, and then we have R, and then we have the T. If not stated, that's 25 degrees Celsius. Okay, so given that, let's plug that into our calculator. Where is my mouse cursor? Okay, so let's plug that into our calculator. Let me just change this. So this is now 0.79, and this thing here should be 2 electrons. Pressing equal sign, we will get 5.12 times 10 raised to 26. Okay, so take note that the K is greater than 1. Okay, so it is way greater than 1. So it means the reaction is spontaneous. It is going to the product side. Okay, so that's how we solve for delta G and K. So again, this is asynchronous anyway, so you can go back to the you can play back the video if you want a slower discussion. Okay, sorry. And now for the last part of our topic, for the last part of this chapter, let's talk about the Nernst equation. Okay, so take note that we have not given yet the equation for non-standard cell potential. We know that standard cell potential is E cathode, E naught cathode minus E naught anode. But I have not given yet the equation for the E cell only, the non-standard. Okay. So if you want to solve for the non-standard cell potential, meaning that the concentration or the pressure is not equal to 1, then we have to use the Nernst equation. Okay, so we have to use the Nernst equation. How is this derived? Okay, so according to thermodynamics, let me go through the derivation first. Okay, so we can justify the equation that we're going to use. Okay, so let's derive this first. Okay, so according to thermodynamics, the relationship of standard and non-standard states are given as this. We have delta G equals delta G naught plus RT ln Q. What is Q? Remember, we have K and Q. Q is the reaction quotient. Okay. So in our discussion, we know that delta G is negative NF E cell, right? So let's plug it here. We have negative NF E cell. Then for the other one, we have negative NF E naught cell. And take note of the difference. We have to emphasize that this is non-standard, and we have to emphasize that this one is the standard. Okay. Plus RT ln the reaction quotient. Now, if we divide both sides by 1 over negative NF, okay, so if we divide both sides by 1 over, if we divide both sides by negative NF, okay, we will get what? Okay, we can cancel this, we can cancel that, giving us the final equation: E cell equals E naught cell minus RT over NF ln Q. Okay, so that is just how we derive the non-standard cell potential from the free energy. Okay, so when are we going to use this? We are going to use this, okay, if we have non-standard condition. So meaning that the concentration is no longer equal to 1, the pressure is no longer equal to 1, or the temperature is no longer equal to 25 degrees Celsius. Okay? So if any of those three categories has been violated, then we have to use this Nernst equation. Okay, again, take note that Q is the reaction quotient. It has the same expression as the K. That's also product over reactants. So the same rule for equilibrium constant applies to K. So now let's answer some basic problems. By the way, remember that we have constants here. We have the R, the T, and the F. Okay, so we can actually combine them. Okay? So remember that R is 8.314, and then we have T, which is 298.15, and then we have the F, which is 96485. We can combine this as 8.314 to 98.15 divided by 96485. We can combine that as 0. E cell equals E naught cell 0.0256 over N ln Q. Okay, so we can combine all the R, all the constants, given that the temperature is 25 degrees Celsius. We can combine all of them as this. Okay, so we can use that. Yeah, so that's 257. I'm sorry, I have not rounded it off. But the common thing that we use in chemistry is the one that is in the logarithm function. Okay, so we commonly use the one in the log function. So how can we derive this from this? Okay, so how do we get that? So if you want to express ln Q to log, okay, all you have to do is to divide it by the log of the Euler's number. Okay, just some algebra stuff. Okay, so meaning if I have 0.0257 over n, then to get the log version, that is just 0.0257 over n log e. Log e is a constant. If you plug this into your calculator, this will become 0.0592 over n log q. Okay? And that is how we ended up with this one. So which are we going to use? We prefer to use this one. Okay. We commonly use the log function. Okay, because the curve of the log function has better qualities than ln. Okay, so that is according to the textbook, but actually you can use any of those, but again it will be better if we just agree to use this one anyway. Okay, but they will still yield the same answer. Okay, even if you use this or this. Anyway, so let's proceed with some questions. I'm not going to answer all of this, as I'm just going to answer two. Again, I already uploaded the answers on Canvas. Please download them. But let me just explain how I ended up with those answers. Okay. So let's look at this problem. We have to calculate for the E cell of the reaction given below. given that the concentration of cobalt 2 plus is 0.25 molar and the concentration of iron 2 plus is 0.94 molar. Okay, so since the concentrations is not 1, okay, so this is not 1 molar, this is also not 1 molar, that means I have to use the Nernst equation. And so again, if the concentrations are not 1 molar in quantity or in value, then that means you have to use the Nernst equation. So we have E cell equals E naught cell minus 0.0592 over N log Q. Okay, so we have to use this. Okay, so based on the reaction, we can now write the Q. Okay, so we can write the Q as the concentration with the products over the reactants. Again, take note that solids are not to be written on the expression for Q or K. Okay, so that means we're just going to include cobalt 2 plus and iron 2 plus. Okay, so now we know the Q. The next thing we have to do is to find the E naught cell. Okay, we know the equation for E naught cell. This is just the E naught cathode minus E naught anode. By looking at the equation, so you can actually confirm this. Which one is the cathode? The reduction. So this one is the reduction. This is the cathode, and this one is the anode. Okay. So let's look at the potential for iron 2 plus to iron. So let me just look through this table. Iron 2 plus to iron. Where is it? I don't know. Okay, so here it is. So it's 0.44 negative. No, it's negative 0.44 volts. Okay. For the anode, we have the oxidation of cobalt to cobalt 2 plus. Okay, so let's look at this table. Okay, so looking at this table, cobalt is yeah, so it's here. It's negative 0.28. Okay, it's negative 0.28 volts. So obtaining the E naught cell, the standard cell potential, that's negative 0.44 minus negative 0.28, which is 0.16 negative. Okay, so that's negative 0.16 volts. So that means this reaction is non-standard. I mean, the reaction is non-spontaneous. Okay, so we now know the E naught cell, that is negative 0.16. Let us plug it there. And let me just plug it in there. How about the N? The N is the moles of electrons. So the moles of electrons can be obtained when we balance the equation. Okay, so let me rebalance the equation again. So again, we separate this into two half equations. So we have cobalt 2 plus. You add 2 electrons here, so the equation is equation now is balanced. You have Fe2 plus and then Fe, add 2 electrons here. Okay, so combining them, you can see that the mole of electron is 2. Okay, we have 2 electrons here, 2 electrons there, so we're going to use 2. Okay, so that's how you get the givens, the given from the equation. So this N is now 2. Okay, so what else? So we now know the E naught cell, which is negative 0.16. We now know the N, which is 2. When we rebalance the equation, we can just see that the moles of electron is 2. And then we have the concentrations. We have the expression for the Q. product over reactant. So that's cobalt 2 plus divided by iron 2 plus. Take note that the solids has should not be written. Okay. So now we can plug in the concentration of cobalt and iron. Okay. So the concentration of cobalt is 0.25 and the concentration of iron is 0.94. Okay. So if we plug this into our calculator, we can get the E cell, the non-standard cell potential. Okay. So allow me to show you how to plug this into your calculator. So here we go. Let me erase this. We type in first the E naught cell minus, we have 0.0592 over 2 followed by log. On the numerator we have 0.25 and on the denominator we have 0.94. Okay, so the E cell is 0.14 negative volt. So again, this is how you plug it in your calculator. E naught cell minus 0.0592 over mole of electron logarithm products over reactants, negative 0.14 volts. So what you can see is that by changing the concentration, you can change the potential of the cell. Okay, and this is what actually the pH meter is doing. Okay, so what the pH meter is actually doing is that it determines the E cell, and from the E cell, it solves for the concentration of H plus in the solution. Okay, so it is programmed to solve for the concentration of H plus using the Nernst equation. Okay, and then if it got the concentration of H plus, then it all it has to do is to just get the negative log of that. Then it will report the pH value. So this is the thing that the um, pH meters are doing. Okay, so this is what they do. They use the Nernst equation. By comparing the voltages, you can get the concentrations, and vice versa. By determining the concentration, you can determine the E cell. Okay, so that's one. I will leave this to you to practice. However, this is solved in the worksheet. Okay, so this will be the last one. Okay, so this will be the last one. This is a very lengthy. Uh, this is a very lengthy question. Anyway, so let's answer this. So consider the galvanic cell below. Okay. Uh, in a certain experiment, the EMF of the cell is found to be 0.54 volts at 25 degrees Celsius. Suppose that zinc 2 plus is equal to 2.5 molar and the pressure of hydrogen gas is 1 atm. What is the pH of the solution? So as you can see, it is obvious that the concentrations, okay, so this concentration is not equal to 1, although this pressure is equal to 1, this temperature is 25, but again, the concentration is not equal to 1, so we have to use the Nernst equation. Okay, so if one concentration is not not equal to 1, then you have to use the Nernst equation. Okay, so let's write the Nernst equation for this problem. We have E cell equals E naught cell minus 0.0592 over n log Q. Okay, so take note that Q is the reaction quotient. Remember that in chapter 4, we separately write the pressure and the concentration values, right? So we write the K expression for pressure separately from the K expression for the pressure. Okay, So we write Kc and Kp. But for this topic, uh, we are just going to combine them. Okay, so we are combining the pressure and the concentration. Okay, because actually Q doesn't care. Q doesn't care whether that's aqueous or in gas phase. Okay, so you just have to multiply the pressure and the concentration at the same time. Let me do that. Yeah, so what I mean is that you have on the product side, you have zinc 2 plus, and then you also have the pressure of hydrogen gas. Again, this is not done in chapter 4 because you know there's an expression for Kp and Kc, but for this topic, we are going to combine the concentration and the pressure. We combine them into Q, okay? And then on the denominator, you have zinc solid, which is not to be written. Then we have the H plus. We have the H plus. Now take note, it is a coefficient of 2, so it has to be squared. Before anything else, let us derive first an equation to get H plus. Okay, let us derive first how to get H plus. Take note that H plus is inside the log function. So let me derive how to solve for that first. You transpose this on the other side, so you will get E cell minus E naught cell, okay, uh, equals negative 0.0592 over N log zinc 2 plus pressure H2, H plus squared. And then we have to cross multiply the coefficient before the log function. We have to cross multiply that. We will get negative N E cell minus E naught cell over 0.0592 log zinc 2 plus pH2 H plus squared. Okay, so let me erase this. What I'm doing is I'm deriving an equation in terms of H plus. So I'm going to get H plus out of the log function. How do you do that? By doing the anti-log, okay? So we make the equations an exponent of base 10. So this will now be equal. Take note that the log will cancel out, okay? So I'm not going to write the log anymore. They will be canceled out. This is the concentration of zinc 2 plus, pressure ups, I'm sorry. So it should be the pressure of H2 only, and the concentration of H plus squared. So by cross multiplying this, by cross multiplying that, I will get H plus squared equals concentration of zinc 2 plus pressure of H2 divided by 10 raised to negative N E cell minus E naught cell over 0.0592. But take note that H is squared. No, so H is squared, so you get the square root. Okay, so you just get the square root, so you can solve for the H alone. There you go. So this is the equation that we are going to use when solving for the H plus. But the problem asks for pH. So after you solve for H plus, you just get its negative log. Okay. Oops, I'm sorry. Let me rewrite the equation here. That's H plus equals the square root of zinc 2 plus pressure of hydrogen gas 10 raised to negative N E cell minus E naught cell over 0.0592592. So that's the equation we're going to use. Now let's solve for the E cell. Okay, let's solve for the E naught cell. So according to this problem, the EMF is the electromotive force electromotive force, which is basically E cell. Okay. So whenever you see EMF, that is just the E cell. Okay. So according to this problem, E cell or the EMF is 0.54 volts. Okay. So we have E cell now. Okay, we have the concentration of zinc and the pressure of hydrogen gas. So let's solve for the E naught cell. How do you solve for the E naught cell? E naught cell, remember that's E naught cathode minus E naught anode. Okay. So by looking at the equation, our cathode is the H plus to H2. Okay. So this is the cathode reaction. Balance this, you will get 2 electrons. And the anode one is the zinc to zinc 2 plus. So I'm expecting as of this point, you can check which one is the oxidation, which is the reduction, by just looking at the equation. Okay. So I hope you can do that. Okay. And take note, the mole of electron is 2. Okay. So let's look at the table. Let me pull up my SRP table here. So for hydrogen, that's 0 volts. Okay. Remember the standard hydrogen electrode, it has a potential of 0, and that's the basis for all this measurement. For zinc, that's negative 0.76. Okay. Okay. So negative 0.76. So the cathode is the hydrogen, which is 0, minus negative 0.76 for the zinc. So the E naught cell is 0.76 volts. So we now know the E cell. We also know the E naught cell. This can be calculated in the table. And by balancing the equation, we get the N. Okay? The problem gave us the concentration for zinc and the pressure of the gas. So basically, we can solve for the H now. So let's plug in all this info into our equation. So let me rewrite it here. By the way, my discussion is quite fast, okay? So if you don't follow, just play back this video, okay? So the concentration of zinc is 2.5 molar. The pressure of hydrogen gas is 1 atm. And then on the denominator, we have 10 raised to negative. The mole of electron is 2. E cell is 0.54 minus E naught cell, which is 0.76. The denominator is the 0.0592. Okay. So let's plug that in our calculator. Let me pull up my calculator here. By the way, I'm not going to fully explain how we got that. That's just basic algebra. But if you want to rewatch this video, then please do. Okay. So this is 2.5 times 1 divided by 10 raised to. So we have a negative sign here in front. So that we have 2 times the E cell, which is 0.54 according to the problem, minus the E naught cell, which we calculated as 0.76 over 0.08. I'm sorry, 0.0592. So this is the concentration of H plus. So it's 3.04 times 10 raised to negative 4 molar. Okay. So again, so if you want to watch how I typed it in the calculator, just play back. Okay. So just a few seconds ago. Anyway, so we got the concentration of H plus equal to 3.04 times 10 raised to negative 4 molar. So to get the pH of the solution, So to get the pH of the solution, all we have to do is to get the negative log of that. Negative log of 3.04 times 10 raised to negative 4 molar. You should not write the unit, okay? Sorry for that. Okay, so let's get the negative log of this answer. Negative log of our answer will give us the pH equal to 3.52. Okay. So the pH of the solution is 3.52. That is how you get the pH of the solution using the Nernst equation. Okay, and this is what the pH meter does. Okay, so this is what they do. They compare the standard cell potential with the non-standard cell potential, and then it uses this equation to get the concentration of H, and then this concentration is plugged into the negative log function, giving us the pH reading. So this is what the pH meter is doing. Okay, so with that, we're done with chapter 6. Okay, so we are done with chapter 6. So I expect that as of this point, you can now answer the quiz. I uploaded the quiz, and it will be open starting today, Monday, until Thursday. Okay, so please answer the, please use the worksheet as guides. Use them as guides for your practice. Anyway, the calculation part in the quiz is based on the worksheet. Okay, so just be familiar on the steps, on the processes that I have written in the worksheet. Okay, so with that, thank you for attending our asynchronous discussion. So on Thursday, Friday, that will be our last session. I mean, last synchronous session. So that will be the last time that we will meet face to face. Okay. So after that, we are going to have another asynchronous discussion for chapter 8. Then we will have the final examination. Okay. So thank you very much for watching this video, and I hope you learned something. If you have any clarification, just message me on MS Teams. I'll see you again on Thursday and Friday. Goodbye.